Welcome to The Explainer. Today we're going to demystify the absolutely fascinating and honestly pretty complex physical and industrial processes behind how everyday foods are actually made. Think about that jar of instant coffee sitting on your counter right now, or those raisins shoved in the back of your pantry.
Let's dive right into this everyday enigma. Have you ever actually stopped to wonder how a splash of liquid milk magically becomes a fine powder? Or why a juicy grape turns into a raisin that can literally sit on a shelf for months and months without rotting? Well, today we are exploring the microscopic, totally invisible forces that keep the food in our kitchens safe, compact, and, most importantly, delicious.
Here's our roadmap for today's Explainer. We're going to start with the magic of dehydration, explore the science of air, dive into the mechanics of moisture, map out the drying curve, and then finally, wrap up with industrial drying technologies. All right, Section 1, the magic of dehydration and how we turn back the clock on spoilage.
So the absolute crucial point here is that true dehydration requires controlled heat to remove water. According to our source material, this specifically involves evaporation or sublimation, and it excludes things like baking or mechanical membrane separation, mostly because those processes remove a lot less water. Now, what's the main goal? Extending shelf life. By removing water, we lower what's called the water activity of the food. It's a brilliant mechanism. It strongly inhibits microbial growth and practically stops enzyme activity. But, and this is a big but, it doesn't actually kill or inactivate them. If moisture ever creeps back in during storage, boom, rapid spoilage kicks right back off.
Beyond just preservation, dehydration gives us this incredible reduction in the weight and bulk of food. This is exactly what gives us those highly convenient, easy-to-handle ingredients we use every single day. We're talking instant coffee, dry pasta, egg powders, spices, the whole shebang. But it is a super delicate balancing act. Food scientists have to carefully dial in the perfect drying conditions for individual foods, because if they get it wrong, you end up with a severe deterioration of eating quality and a massive loss of nutritional value.
Moving right along to Section 2, the science of air, the invisible medium doing all the heavy lifting. To understand how this works, engineers use something called a psychrometric chart. I know, it sounds intense, but psychrometry is actually just the study of the interrelated properties of air and water vapor. Based on standard barometric pressure, this chart maps out the secret factors that completely control a system's drying capacity. Basically, there are three main things at play here: the amount of water vapor already carried by the air temperature, and the overall volume of air passing over the food. To actually make sense of those factors, we have to compare two specific types of temperature. First up is the standard dry bulb temperature. That's just what a regular, everyday thermometer reads. But if you wrap that thermometer's bulb in a wet cloth, you get the wet bulb temperature. Here's why it matters. As water evaporates from that cloth, it absorbs latent heat, which physically causes the temperature reading to fall. By looking at the difference between those two temperatures, engineers can calculate the relative humidity of the air. And from there, they know exactly how much more water that air can suck out of a piece of food. Next up, Section 3, the mechanics of moisture. Let's take a microscopic journey. Imagine the totally invisible, microscopic battlefield happening inside our food right now. The challenge is that water is trying to move from inside the food cells out into the surrounding air. And when hot air blows over wet food, the water vapor doesn't just freely float away. No way. It has to fight through this boundary film of air that completely surrounds the food. You can think of this film as a literal physical barrier. It blocks heat transfer trying to get in, and it stubbornly traps water vapor trying to get out. To win this battle, engineers rely on three main characteristics of the air: moderately high temperature, low relative humidity, and high air velocity. When you combine these, it creates a powerful water vapor pressure gradient. That gradient is the ultimate driving force, pulling moisture from the wet interior to the dry exterior. Basically, the faster that hot air blows, the thinner that boundary film becomes. A thinner film means less resistance, a much stronger pressure gradient, and moisture being aggressively driven right out of the food. Let's look at Section 4, the drying curve, and its two distinct phases. When we map this entire process out, it creates what's known as a drying curve, which reveals exactly how moisture content drops over time. And it highlights a really fundamental reality of food dehydration. The whole process is actually split into two very distinct phases. Initially, we have what's called the constant rate period. During this phase, moisture is sitting right there on the surface of the food. Evaporation is fast, it's easy, and it acts a lot like water just evaporating from a puddle. But eventually, we hit a wall.
That's the falling rate period. The surface dries out entirely, and now the water has to seriously struggle to move from the deep interior of the food out to the surface. It relies on really slow, tedious processes like capillary forces and liquid diffusion. This falling rate period, it's usually the absolute longest, most stubborn part of the entire drying operation.
And you know, this is exactly why smaller food pieces dry so much faster. Think about drying crushed herbs versus big, thick, whole leaves. In that easy, constant rate period, smaller pieces offer a vastly larger surface area for evaporation. And during that super difficult falling rate period, smaller pieces mean a much shorter distance for that trapped internal moisture to travel to escape.
All right, final section. Section 5. Industrial drying technologies and commercial scale tech. To actually manage all of this thermodynamics at a massive commercial scale, engineers have designed some incredibly specific tools to maximize surface area and airflow. We've got massive bin dryers, which are often used for finishing products by blowing air up through deep beds of food. There are cabinet or tray dryers. They're pretty flexible, but honestly, they can sometimes yield variable quality if the air isn't distributed perfectly. Then you have fluidized beds. These are awesome. They blow hot air from below with such force that they actually suspend and vigorously agitate pieces of food right in midair. We even have foam mat drying. That's where liquid food is whipped up into a foam to vastly increase its surface area, which makes it dry up to 3 times faster than a standard liquid. But what about pure liquids like milk or instant coffee? For those, we use massive spray dryers. The real secret weapon here lies in the atomizers. We're talking centrifugal rotating discs, high-pressure nozzles, 2 fluid nozzles that use compressed air, or even ultrasonic nozzles powered by sound energy. These atomizers literally blast the liquid into millions of tiny droplets, sometimes as small as 50 microns in diameter. Because the droplets are just microscopic, their surface area is totally maximized, and they dry into a powder almost instantaneously inside the hot air chamber.
All of this incredible technology, all of this super precise control of air velocity and humidity exists because of one inescapable scientific truth from our sources. Most heat damage to food can occur in the falling rate period. Remember that stubborn phase? If the water isn't escaping fast enough to provide evaporative cooling, the surface temperature of the food will rapidly spike to match the hot air. If engineers don't perfectly dial back the temperature right then, the food's cellular structure, texture, and nutritional value will be permanently destroyed. It really is a beautifully complex dance of thermodynamics and engineering. So the next time you pour a bowl of breakfast cereal, brew a quick cup of instant coffee, or grab a handful of raisins, take a second to appreciate the totally invisible journey it took to get there. What other marvels of microscopic physics are hiding right there on your kitchen shelf? Keep wondering, and we'll see you in the next explainer.